Today we're going to learn how to find the domain from an equation. This is really coming from section 2's homework. However, the problems in the homework for 2.2, the problems that are in that homework are harder than what you're going to see on the test. So this is why I'm going to give you a bunch of examples that I'm going to do in the video. Now, I'm probably not going to get through all of them with you, but I will make a video of all of them, and then tomorrow I'm going to practice this some more with you. Now, when we covered these basic functions in section 2.5, does anybody remember what the domain of a quadratic function is?
All real numbers.
All real numbers. Remember that u gets bigger and wider. So this one, you're always going to start out by thinking the domain is always all real numbers. There's only going to be 3 scenarios when we're going to exclude numbers. One of the scenarios is when it's a fraction, because what wouldn't work in a fraction? So like, let's say I have 1 over x. Anything that makes the denominator a 0. The other thing we're going to check for are square roots. We don't want any imaginary numbers, so all of our square roots have to be positive numbers. Other than that, your domain is always all real numbers. So this domain, and we're writing it in interval notation, is all real numbers. You need to remember that the graph of the quadratic function, whenever you see an x squared, is always going to be all real numbers. Back. So my second example here, anybody remember me telling you the domain for the x cubed graph? All real numbers again. Remember, this looks like this, and eventually it's going to cover the whole x-axis. So domain for the cube function is all real numbers. All right, so here's our first exception. What would make this function not work?
0.
Exactly. So when you have a fraction, you take the denominator and you're going to set it not equal to 0, because this is what x can't be. And written in interval notation, we're going to exclude the 0. So if this were on a number line, it would have a hole here at 0, but then it would go from negative infinity to positive infinity. So everything, but it jumps over the 0. The way that we would write this is negative infinity up to the 0, jump over the 0, so we'll union that. Then when we get on the other side, we start again and go to infinity. Another fraction. Again, we're going to set that denominator not equal to 0. And I can solve this 2 ways. I can either factor it, or I can use the square root method. I don't care which method you use. We just have to solve. X plus 2 not equal to 0. X minus 2 not equal to 0. So x cannot be negative 2, and x can't be positive 2. If you use the square root method, you would add 4 to both sides, and then square root, and plus and minus 2. Either way. So again, we're going to write the domain in interval notation. It's got a hole here at negative 2, a hole at positive 2, and then otherwise it's every other part of the number line. So again, where these holes are, that's where my u's are going to be. So it's going to go from negative infinity. It's going to put on the brakes at negative 2. Jump over the negative 2, start up again on this side, jump over it, start up again, and then go to infinity. Another fraction. Okay, now we're only testing for numbers to exclude that are real. Watch what happens when I do this one. When I move the 1 over, I get square root x is equal to plus and minus I. I don't care about excluding i's, so my domain here is all real numbers. So if you get an imaginary solution, we don't care about excluding it. It's going to be all real numbers. Next one is a radical. For radicals, we don't want negative numbers. So when we have a square root, we take what's underneath it and make it greater than or equal to 0, because I don't want a negative number. And again, in interval notation, this would look like a bracket pointing this way. So from 0 with a bracket to infinity. Let's continue on. Let's try just a radical, no fraction here. Again, remember we want the domain only to be positive. So if I take what's under the square root, x minus 1 needs to be greater than or equal to 0. I'm going to add 1 to both sides. X must be greater than or equal to 1. And again, if you wanted to see this on a number line, put 1 here. It's got the bracket going to infinity. So in interval notation, it would be positive 1 with a bracket going to infinity. Let's try the next one. Again, for my denominator, we know it can't be 0, and we also have to make sure that it's positive. So I'm just going to set what's under the radical in the denominator greater than 0. So when you have a fraction and there is a radical in the denominator, we're not going to set it greater than or equal to 0, just greater than, because we take away the or equal to part because the denominator cannot equal 0. So this, written in interval notation, would be from 0 to infinity. Let's try another one. This time I have a fraction, and I also have a radical in the numerator. So let's go ahead and start with the radical. So again, we're going to take what's underneath the square root, and we know that it needs to be greater than or equal to 0. It needs to be positive. Subtract. X needs to be greater than or equal to negative 1. And now let's go ahead and start with, or work with the denominator. X squared minus 4 cannot equal 0. I'll go ahead and just use my square root method. X squared equals 4. Apply the square root method. X cannot be equal to plus and minus 2. So let's go ahead and take a look at this on a number line. -2, -1, +2. I know when x equals +2 or -2, it'll be a hole in the graph. And then as far as this goes, I'm going to go ahead and put my closed circle on -1, and it would be all values greater than -1. So again, I need to only see where, so for my numerator, it's all real numbers except when, or no, for the numerator, it's all real numbers that are greater than or equal to -1. For the denominator, it would be all real numbers except -2 and +2. And again, we need to see the overlap. So for the denominator, it would be this up to here and here. And again, I need the intersection. So it's going to be this, but we jump over the hole. So let's go ahead and write this in interval notation. It's going to be from -1 with a bracket up to the 2 where there is the hole, where it's not equal to, with a parentheses. The hole will be the union. We jump over it and then start up again and then go to infinity. For the next one, the only thing I need to check here is the denominator. So again, take what's under the radical, 3x minus 3 minus 2x, and again, it has to be greater than 0. It can't equal 0 because it's in the bottom of a fraction. 2x is greater than -3. divide by negative 2. Because I divided by negative, I need to reverse the symbol. And now this becomes positive 3/2. So again, if you wanted to see it on a number line, 3/2 is here, open circle, going to the left. You can also show it with a parentheses. So again, it's pointing to negative infinity. So negative infinity up to 3/2, and again, just parentheses, no brackets. Let's try another one. This time it is the cubed root. Remember from section 2.5, there weren't any restrictions on this, so this is going to be all real numbers because we can find a negative cubed root. If you weren't sure, let's go ahead and make our little chart here. If I plug in negative 8 and I find the cube root of that, I can get negative 2. If I do positive 8, I can also get an answer. It's positive 2. 0, cube root of 0, again, is also 0. So there are no restrictions here. The domain is all real numbers. Now, however, we've moved the cubed root to the bottom of a fraction. We do not want it to be 0, otherwise my answer is undefined. So again, here, x can't be 0. So if we were to put this on our number line, this is where the hole would occur. It can't equal 0. Otherwise, it's all real numbers. So we would write it from negative infinity up to the 0, union that, in other words, jump over the hole, go back, and go to infinity. Let's try another one. Here I've got two radicals, so I need to test both. So for the numerator, the 2x minus 1, notice the restrictions here. It has to be positive, so I need to make sure that it is greater than or equal to 0. For the denominator, it must be greater than 0. So I'm going to solve each. I'm going to add 1. 2x is greater than or equal to 1. Divide by 2, and x is greater than or equal to 1/2. I'm going to do the same thing for the denominator. I'm dividing by a negative, so I need to remember to reverse my symbol, and negative divided by a negative is a positive. So now here, it's going to be important that we look at this on a graph. So I'm going to put the 1/3 and then the 1/2. So if I go to graph this one, x is greater than or equal to 1/2, closed circle, going to the right. This one is going to be an open circle going to the left. Now remember, when we're looking for our domain values, we're looking to see where the graph overlaps, so where the blue and the green would both be at the same time. And notice there are no values of x that would satisfy this function, so this one is undefined or no solution, because there are no values of x that will make this function work. Now number 14 is a little variation of this. Again, we have the same numerator. We already solved it, so we did it right here. So we know x has to be greater than or equal to 1/2. Now let's take care of the denominator. So 3x minus 1, again, we do not want a 0, and we also want it to be positive because it's under the radical. Let's go ahead and solve this one. I'm going to add 1. 3x is greater than 1. Divide by 3. X is greater than 1/3. So now this one actually is going to give us an overlap. So if I graph the first one, the 1/3 in the blue, and then I'll graph the 1/2. So here would be an open circle going to the right, and then now this one, closed circle right here, also going to the right. So again, you can see where it starts to overlap is right here. So in interval notation, 1/2 with a bracket, because it includes it, it's a closed circle going to infinity. So those are the end of the examples of finding a domain from an equation. We will practice this some more tomorrow. This is on your test. I know there is no homework problems, but there are homework questions in the review that we are going to post.